Okay, so let me start. So before continuing with series, I'll just briefly go back to the set of extended reals and just recall one or two things. So I mentioned that the algebraic operations, when you extend to the extended reals, they don't extend very satisfactorily. So you can only extend them partially. So I'll just write down here the algebraic operations on the extended reals, which are defined, which are not defined. So as far as addition is concerned, if A is any real and you add plus infinity to it, what you get is plus infinity. Similarly, if you add minus infinity, you will get minus infinity. And it's the same if you do it in the other order because it's commutative. Okay. Plus infinity plus infinity, this is also defined. This is plus infinity, minus infinity, this is defined, this is this. What is left undefined is these two quantities as far as addition is concerned. When it comes to product, the multiplication, so what are the rules? If you multiply a real with, so A is going to be always real, plus infinity or minus infinity, this would give you plus infinity if A is a positive real and rather plus infinity and minus infinity respectively if A is a positive real, and minus infinity plus infinity depending on whether you have plus infinity or minus infinity on the left side if A is negative. And the same for the two coming in the opposite order. And what about this product? This is plus infinity, which is also this. And what is left undefined are the products and also the same product in the other order, opposite order. So these are the two things left undefined here. These are the two things. And division, which basically comes from multiplication, but there also on the extended reals, one has to be careful. So if A is a real, this is defined to be 0, and here it would be like the case of multiplication. If A is positive, then it would be plus infinity or minus infinity exactly. And if A is negative, they would get, the signs would get reversed. So in this case, what are left undefined are one of the infinities by another infinity and by 0. Okay. So now let me get back to series. We are discussing series. So last thing we talked about was power series in X, which means basically you look at a series of this special form where the nth term looks like this. It's some real times this particular number to the power n. And then we have seen that we can give a, using the comparison test, comparison with the geometric series essentially, or the root test if you like. One can give a quite precise rule for convergence. So, and that is the following. If mod x is less than 1 over this, then the series converges absolutely. Absolutely. Mod x greater than this number, it does not converge. And at the boundary, that is when you have equality, then either way, it can go either way depending on the specific series you have. Okay, so okay, that reminds me. So I defined what is called absolute convergence of a series, right? Converges absolutely if summation mod an converges. And we have seen examples where, let's say this series, this itself converges, but does not converge absolutely. So such series are called conditionally convergent. So conditionally convergent if this converges but does not converge. So this is an example of a conditionally convergent series. Okay, now let's say you have two series, summation a and summation b, and that means the terms here are a0, a1, a2, and so on. And here the terms are b0, b1, b2, and so on. Okay. Now the product of these two series, or you can simply say product, or you can say Cauchy product. So this is a series whose nth term is given by, so it's not term-wise product. It's Cn is not a and bn. This product is slightly different. This product is like the nth term is going to be, so let's say you're looking at the nth, the terms up to the nth term. So nth term would be product of these two, product of these two, product of these two, and so on. So, and finally product of these two, that is a0 bn plus a1 bn minus 1, and so on, going all the way up to an, and with an will come b0, so which is ak bn minus k equal to 0 to n. Okay, the Cauchy product of this is the series summation Cn, where Cn is given by this. Now, then the next question is, suppose you are given two series, you know something about their convergence, whether we can say anything about the convergence of the product series. So here I'll just state the result. I won't write down the proof in detail, but I'll probably I'll post a proof on the course page. But for the purpose of the exam, you did not try to memorize the proof. You can go through it. You can try to understand what is being done there. But more important here is the result itself. So which I'll state now. So if both the series converge and one of them, and one in the sense of at least one of them converges absolutely, then the product series converges. Okay. So we'll look at now examples and how this result is going to be useful for us. So what are the examples of series we have seen? First of all, in the last class, we have seen some important examples. What are those examples?
Exponential.
Right. So some functions we got as power series, right? Those are all infinite series. And they also, we have seen that they also, all those three at least, the series for sine x, series for cos x, and series for exponential x, they all converge absolutely on the entire real line. So they satisfy the hypothesis here. So we can see what we get if we apply this result. So let's first take this series. Okay, so let's say this is the series, its sum is a number which are just denoting by this. Okay. Let's take essentially the same series, but for a different number here. Okay. Now let's see what is the product of these two series. So what would be the nth term of the product series? So the nth term of the product series is going to be the kth term from here n minus kth term from here, and then you sum over k from 0 to n. And what is this sum? So what you can do is you can multiply and divide by factorial n. Then you have, once you do that, you have n choose k here, the factorial n in the numerator, and these two together give you n choose k. And you have x to the power k, y to the power n minus k. And this is the sum here is from k equal to 0 to n. So this is 1 over factorial n x plus y to the power n. And this is exactly the nth term for the series, right? So here, oh, okay, sorry, one thing. So the result that I stated, it is a little bit incomplete. So it of course converges, but also then the product series converges to the product of the sum of those two series. So this is another important part of the result. So here, of course, we know that this series already converges, that we have already checked. So there's nothing new there by applying this result. But what is new here is this part in this case. So it would tell us that, so this is the sum of the first series, sum of the second series, their product would be equal to sum of the product series, which is this. So you have this equation, nice equation that this function is going to satisfy. Okay. Now, similarly, we have seen that this series converges, and the sum we had denoted by sin x. And similarly, this series, we had denoted the sum. This again converges absolutely on the entire real line. This we had denoted by cosine of x, cos x. And you take, x can be any real. So you take another real. You take another real. Okay, so think of the left-hand side as a power series in, or just think of it as a series. Forget about the notion of power series. Now that we know they're convergent, absolutely convergent, and so on. So on the left-hand side, you have a series. The right-hand side is just notation for its sum. That's all. Okay. Now, from your high school mathematics, you have seen this. Right? So now you can actually give a rigorous proof of this. So what you do is, you so sin x, the corresponding series is this, cos y, the corresponding series is here. Okay, so compute the nth term of the product series. Product series. So you will have some series here, summation Cn. Then the same thing you do for this. So sin y, you have a series. So here, and cos x, you have another series. Again, you do the same thing. Compute the nth term of the product series. Call the nth term dn for this. Okay, so here you have called it Cn. Here we'll call it dn. So we have now two series, summation Cn, summation dn. So, and this, I think I may have stated that if you have a series summation Cn, if you have this, then when you look at this series, this would be simply this plus this. So you just look at the partial sums and look at the limits, and it would follow. So you look at summation Cn, this series, summation Dn. So on the right hand side, what you'd get is the sum of this series. Okay, and you will see that this is exactly what you get when you compute Cn, when you compute Dn, which means you are computing nth term Cn plus Dn. That would give you exactly the nth term for the series for sine of x plus y. So this product of two series, the result that I stated in the last page, together with this one will give you a proof of this trigonometric identity. Same way, you can prove cos x cos y plus sin x sin y equal to cos x minus y. Okay, and a corollary of this would be, which again is something you know, when you put y equal to x, you take x and y to be the same real, what you get is, and on the right side you will get cos 0. Now look at the series for cosine. Where is it? Oh, on the left side. Okay. If you look at the series for cosine x, you will see that only the 0th term survives. The other terms all disappear because of this, which means cosine of 0 is 1. So what you get here is this as a consequence of this identity. Okay, now just briefly going back to the statement again. So I'm not getting into the proof, as I mentioned, but what I want to say is the following. So if you look at the condition here imposed on summation n and summation bn, both of them should converge. Okay, but also this additional condition that one of them should converge absolutely. Now that is something that you cannot do away with. If you just take two convergent series, summation n and summation bn, then summation the product series need not converge. So here is an example of that. You take the series 1, okay, so that means you are looking at minus 1 to the power n, this series. Now this converges by what we have done last time, because the signs are alternating, and this nth term, that these are all non-negative if you forget about the sign, this part, and they decrease to 0. So by a theorem that we did last time, this series converges. But this series does not, does not converge absolutely. So if you look at this series, then you can see that 1 over root n plus 1 is greater than 1 over n plus 1. And by comparison test, you get that summation 1 over root n plus 1 will not converge, because we have already seen the behavior of this series. The series diverges to infinity. So by comparison test, the second part of the comparison test, this series diverges. So this series is conditionally convergent. It converges but does not converge absolutely. Okay. Now let's try to look at the product of this series with itself. So what would be the nth term? And here you will have the same thing again. So the product, these two will get paired, this and the previous one, and so on. So so the signs are going to be the same for each term. Now the first term would be then until the first one becomes n plus 1, the second one becomes 1. So this is going to be the nth term of the product series. Now, I'll leave it here, I'll leave it as an exercise. Show that the product series does not converge. Okay, so you have to look at this quantity a little bit more carefully. You have to try to simplify it maybe, or get some estimate, an upper bound, a lower bound, whatever that you have to decide. Okay. So I think for series, that's about it. Okay, so before moving to something new, let me just mention this. I think I may not have mentioned this. I don't remember. So we have looked at this series, right? 1 over. So this is basically, by your notation from last time, this is just this. If you put 1 to the power n above, this is the series you get. Now, this is a very special number. So this is denoted by E. Okay. And by looking at this series, you can derive some simple inequalities like so this again I'll leave as an exercise. So you look at the series, look at the first few terms, and then try to derive it, like try to give a rigorous argument. So in particular, this is something positive. So you can talk about this to the power real. So later on, we'll see that this number that we have talked about, which is the sum of this series, is in fact equal to this number. Okay, to be proved later. And in the proof that earlier, the relation that we derived using product of two series, that will play a very important role. Okay, so now on to new topic. So as I had mentioned in the beginning, our main goal would be basically to study functions from R to R and now we are almost there at that stage. So either R2R or from some defined on some subset of R, sorry, from some subset of R to R. Now for such functions, what we are interested in are limiting behavior of such functions near a point. Behavior of a function near a point. Of course, this is slightly vague right now, but this is what we want to make precise, give meaning to. Okay. So the idea is this, and I think most of you would probably be familiar to various degrees with this notion, the limit of a function near a point A, let's say. So typically one talks about a quantity like this.
Sir, before that, I have a question.
Yeah,
There used to be one formulation of sine and cosine in terms of the triangles, and now we have this particular formulation. So what's is there any connect between the two?
There is a connection, but right now I do not want to get into this. So for that you have to bring in complex numbers, because right now what we have at our disposal is just the real number, the line, right? Okay. Now once you introduce the complex numbers, then you have the plane at your disposal. So there you can make that precise. So you can make a connection between that description and the description that we are looking at now.
Okay, sir. Okay.
So right now you take it as take this as the definition. So this is more analytic definition. Okay.
Okay, sir.
Okay. So this is something that we'll try to give meaning to. So how the function f behaves as you approach this point A. So for example, let's say, I mean, this is something you would have seen. This example you would have seen in probably school. So this is a quantity, the right side, the quantity that I've written, that is defined for x not equal to 2, right? So let's say this is our function. So the function is defined on, so it's defined everywhere except the point 2. Okay, now when x is not equal to 2, you can actually simplify this expression and it becomes x plus 2. So if you draw the graph, it looks like, except that this point is absent because the function is not defined here the way you have defined the function. Now, for this function, you can see that as you get closer and closer to 2, the function behaves in a nice manner, in the sense that it does not vary too much. If you look at the function values, they get closer and closer to the point 4. So this is for this function. Suppose you look at another function, let's say let's say sine 1 over x, where x is not 0 again, because this will not make sense. So how, first of all, how would it look like? Let's first draw a rough picture of its graph. So sine 1 over x. So as x as x grows, you can see that this is positive but shrinks. So sine x should be small for x very large, and then as x gets smaller and smaller, and then becomes, let's say, 2 by pi, it would become 1. And then, so this part you can convince yourself. You will look at the function closely, and then it would fluctuate more and more as you get closer and closer to 0. So now what happens if you try to get close to the point 0? The function values, I mean, they just go crazy, right? They are going from here to here, and as you get closer and closer to 0, they do it more and more rapidly. They just go up and down, up and down, up and down. They don't seem to get close to anywhere. They just keep traveling. So the idea is that in the first case, in this first example, you'd the limit of fx as x goes to 2, that whatever notion we come up with, we should be able to say that it is getting near 4. That means limit of fx as x goes to 2 should be 4 here. Whereas here, it does not seem to exist. That seems natural, something natural to expect. So this is exactly what this notion of limit will do. And for sequences, we have already come across this notion of a limit, and there, I mean, here also the notion is going to be very similar. So here, let me just recall again. When do you say the limit of a sequence is, let's say, x? This we had seen. So the idea was that given any small neighborhood of x, right? Given any epsilon positive, idea was that we should be able to get hold of a big enough n such that beyond that, all the xn's are between these two numbers. Okay, and then when we talked about extended reals, and the topology there, this for all n greater than equal to capital N, that you have seen that basically means that there is a neighborhood of plus infinity such that for all small n belonging to that neighborhood, you can rephrase it that way. So in that sense, it is getting closer to plus infinity. So here also it is going to be the same. So we will say that the limit of function is going to be, let's say, L if, okay, now let's try to write down from what I just said about sequences and what we know about open sets, etc. in R. So here I'm assuming L to be a real, A to be also a real to begin with. So then what should be the definition? What should be the notion that we're trying to make precise. L is this number, A is this point here. Given any neighborhood of L, okay. So for case of sequences, it was a neighborhood of plus infinity. Here is the point A that is of interest for us. So given a neighborhood of L, there should exist a neighborhood of A, but neighborhoods of A look a little different from neighborhoods of plus infinity. So there will be a difference. So given epsilon positive, there should exist a neighborhood of A. Now neighborhood of A, you can write it as A minus delta, A plus delta. So that's how this delta, there exists a delta. But the stress is basically on the interval rather than just this number itself. It's just that this number you are using to specify a neighborhood, open neighborhood of A delta, such that, so as I go along, I'll make some slight adjustments in what I'm writing right now, such that whenever X is in this interval, that is X minus A is less than delta, this should imply the F value should lie between these two numbers. That is, Fx should be within epsilon. That is, Fx minus L should be less than epsilon. Now, roughly this is it. Now the first point here is when you define this notion of a limit. So you are interested in the behavior of the function near the point A. At A, whether it is defined, whether it behaves completely differently, you are not concerned. So when you are talking about a limit as x goes to A, it is the behavior of the function near A, but not at A, is what you are concerned with. So this condition, you modify it slightly. So this should imply this. So at the point A, what happens? You don't care. So this is the, yeah. Did anyone say anything? Any question? Okay. So what I wrote down is the definition of this statement: limit of fx as x goes to A is L. Now, for this, f needs to be defined. So I have not said any much about where f is defined, what A is with respect to that domain, etc. Okay. So right now, we'll just assume that f defined on a okay, as I said, at A, whether f is defined or not, we are not bothered. So we are not going to demand that f is defined on A. So on A, deleted, I mean, this is just a terminology. I'm going to say in a moment what I mean. Open neighborhood of A, which means that it is defined on an interval of the form CD minus A, where A belongs to CD. So you assume that f is defined on one such interval, and then you look at the look at what I've written on the left. That would now make sense. And more generally, so this I do not want to get into much. you can have a function defined on a set that is subset of R, and then you can define this notion whenever A is a limit point of E. What will happen then is, in any neighborhood, there would be plenty of points from E. So it makes sense to look at the behavior of F near A in that case. If A is not a limit point, then what would happen is you take a small enough open set around A, and then there will be no one from E. So it will not make sense to talk about the behavior of F near A in that case. So in general, this limit of fx as x goes to A, one talks about when the point A is a limit point of the set on which f is defined. But to keep things simple for us, we'll assume that f is defined on an open neighborhood around the point A, leaving out the point A itself. I mean, it can be defined on A also, but we don't require that. Okay. And then you have similar but several other definitions. So when do you say this? So let's call this number 1, 2. So when I'm using A, B, etc., A, B, C, D, those are reals. Because these additional points, they have their own notation, plus infinity, minus infinity. Just give me a moment. Sorry. Then the behavior of f near infinity. Behavior of x near minus infinity. So, okay, maybe instead of 1, 2, 3, I should have said 1a, 1b, 1c. So in all 3 cases, in the first 3, we are interested in the behavior of the function near a real, whereas here we are interested in the behavior of f near plus infinity, here behavior of f near minus infinity. So that way they are different, and you have to, in each case, you have to look at 3 sub cases. Some L real, plus infinity, minus infinity. So there would be in all 9 definitions, you can say. So strictly speaking, this should come under 2, 2ABC, 3ABC, and this should be 1B, this should be 1C, and the previous page, this should be 1A. Okay. So near a real, near plus infinity, near minus infinity, and then where does it go to? Depending on that, you have 3 different cases possible. Now, once you understand this case and you know what are the neighborhoods of plus infinity and minus infinity, the other definitions would kind of follow naturally. So let's look at 1b, for example. So the general nature of the definition, so let me, so let me maybe write that at this stage. So right now, what I'll do is I'll use Greek letters instead of Roman. So alpha and beta could stand for any extended real, let's say. So one says that limit of fx as x goes to alpha is beta if given any open neighborhood of alpha, there exists an open neighborhood, maybe I should name them something, open neighborhood U of alpha. There is an open neighborhood V of, no, I'm mixing it up a little bit. So limit of fx is beta. That means what we want is the following, that by bringing x close to alpha, we can make fx get close to beta, okay, as close as one wants, which means given any small open neighborhood of beta, so this is for beta, not for alpha, so this is what would be given to us. This is what this is something over which you won't have any control. This would be given to us. Once this is given to us, then we should be able to produce a neighborhood V of alpha such that x belongs to V, but as I mentioned, we are not interested in the value at the point alpha. So this should imply fx belongs to U. So if you look at the first case, which we have defined, this is exactly the definition. There we have done it in terms of epsilon, delta, etc. But what it says is this: given any open neighborhood U of beta, there is, and if you think of the diagram, then also it would kind of be clear. You have a function f whose graph is this. Now alpha is this point, so alpha could be plus infinity or minus infinity, but alpha is on the domain, basically that's the point. And then you say that limit of fx as x goes to alpha is beta when this happens, when given any u around beta, you are able to choose a v around alpha such that whenever you stay inside this interval, leaving out the point alpha itself, the function values remain here. So that's the general definition which would apply to these all 9 separate cases. Only thing that would change is depending on whether this alpha and beta, they are real or extended real, the neighborhood, the description of the neighborhood would change. So here 1b saying, so let's look at 1b. What would be the definition of this? Given any open neighborhood of plus infinity, there is an open neighborhood V of A such that x belongs to V minus A implies fx belongs to U, right? This is exactly, so here I have not made any change. I've essentially written this, just replacing beta by plus infinity here, alpha by A here. Now, check that this is same as saying the following. Given any real, so any open neighborhood of plus infinity contains something of the form y to infinity, where y is a real. So given any y real, there is a delta positive, because any open neighborhood of v of a would actually contain something of the form a minus delta to a plus delta. So it is that some such delta we are talking about. There is a delta such that x belongs to a minus delta to a plus delta minus a. So this you can rephrase it like the previous case, x minus a less than delta 0 if you want. These are two different ways of saying the same thing, so that does not matter much. This should imply that fx is greater than y. So this would be slightly more practical, in the sense when you're trying to verify things, then this would be more useful. So it is from this form, it is good to write down this equivalent form first. So this would be the definition of this statement, that limit of fx as x goes to a is plus infinity. So similarly, what I would suggest is write down the precise definitions in all the other cases, which means 1c, then 2a to 2c, and 3a to 3c. Okay. Now, now okay, let's just look at one thing, one statement, just as an illustration of something. So let's say I write this statement. So what such a statement would mean is that one of two things: either this limit does not exist, or this limit exists but different from L. Okay, so since I've made this statement, I should actually first say what I mean by this. So if exists, if is equal to beta for some beta in R bar. So this is just terminology usage. So what I had defined, I mean, only one case, but the remaining cases one has to write down, is a statement like this. Now, if that happens for some beta, then you simply say that it exists without specifying the value. Now, what I'm saying here is that when one writes such a statement, this is not equal to L, then it can mean one of these two things. Either this does not exist at all, or this exists but is different from L. Okay, now looking at the definition of the first case, 1a, so can you characterize it using, say, can you describe this exactly when this would happen using, let's say, epsilon and delta? Like, what would be the, so this is basically negation of the negation of this statement. So what I'm asking is, what exactly is the negation of this? You look at the definition and then see what would be the negation of this statement.
So existence of an epsilon.
Yeah.
That for every delta, the condition fails.
Okay, so let me get there. So let me first reproduce the meaning of this, and as per our definition, that for any epsilon positive, there exists a delta positive such that this is less than epsilon for all x belonging to a minus delta to a plus delta minus a. So something happens for every epsilon positive. So the negation would be that there exists epsilon positive for which the next part is not true. Okay, so there exists epsilon such that this next part does not hold. So now you focus your attention to part 2. 2 is this. So what is not 2? 2 does not hold. So 2 says that there is a delta for which something holds. Okay, so the negation of 2 is for every delta, the next part fails. Now, how does this part fail to hold?
There exists x in the interval such that,
yeah. Okay, so like this, if you break down a statement, you can write down what its negation is. So going by the definition, if you have to show that limit of fx is not equal to L, then this is what you have to do. That you have to produce an epsilon positive such that for every delta positive, there is an x in that interval for which this inequality holds. Okay, so in practice, it is not that useful in most cases, and that's why you need to develop machinery. You develop tools so that you can do it in a simpler way. So okay, so for that, let's first do something. So now we have talked about limit of a function near a point as x goes to a point, and earlier we had talked about limit of a sequence. That was a slightly different notion, but it was, in a way, it was similar because sequence is after all a function. So it was like behavior of that function near infinity. But even so, sequences are rather like convenient objects to deal with rather than a function. So you try and see if we can you can relate the two, meaning you can use the earlier notion here. Okay, so let's assume this. So suppose we have a function defined in a neighborhood of A, and we are told that limit of fx is L. Okay, so going by the definition, if we take any neighborhood of L here, you would get a corresponding neighborhood here, so that whenever you stay in this neighborhood, the values are going to stay within that neighborhood of L. Okay, so now let's use this for, let's say, epsilon equal to 1. So given this epsilon, there would exist a delta 1 such that whenever you are between a minus delta 1 and a plus delta 1, you are going to be between L minus 1 and L plus 1. So let's pick some point in that neighborhood other than A, and let's call it x1. Next, you take epsilon equal to half. So you get a slightly smaller neighborhood here. But for that neighborhood also, you will get a neighborhood of A. So let's say A minus delta 2 to A plus delta 2. So that whenever you stay in that neighborhood, you are now in this area. So such that x belongs to A minus delta 2, A plus delta 2 minus A would imply fx minus L less than half. So now pick an x2 from this interval. So that this way you keep picking x1, x2, x3, etc. These will all be in the domain of f. Okay. And what is special about the xi minus a is less than delta I, whatever delta I was. And what else? fxi minus a, not a, L is less than 1 over I. Okay, so we have so first of all, what happens to this sequence?
Converges to L.
This will converge to L. Okay. Now, so this is right now, this is just an observation. Now, what I want to say is the following. And looking at that, you can see that xi's are also, they seem to be getting close to A. Okay. Now, whether they're going to 0, that we do not know entirely because we don't know what the delta is here are. But this observation is fine nevertheless. So now what we'll do is use this observation. Give me a moment, 1 second, sorry. Okay, so now what we'll do is we'll take a sequence xn in the domain. Domain of f such that xn converge to a. Okay, and also xn not equal to a. Choose one such sequence. We are assuming that f is defined in a open neighborhood containing a, I mean, without the point a, or even in the general case, which we are not talking about really, but even there, a is a limit point of e and of the domain. So even there, we know that there is a sequence in the domain which would converge to a, and the term whose terms are all different from a. So this is something that we can do. We can look at such a sequence. So let's look at such a sequence, and then what happens? So I'll just restate what we did in the last page. So a is this, and now we have a sequence already to start with. Okay, now you look at, just do as before, epsilon equal to 1. So you are looking at this interval around L. So there would exist a delta 1 such that whenever you are here, your values are here. In particular, okay, not yet. Okay, now given this delta 1, since xn converge to a, there would exist n1 such that xn1 minus a would be less than delta 1. Okay, this you can ensure because xn's are converging to a. Now, what happens for this xn1? If xn1, that would be within one distance, because xn1 is here, its value lies in this interval. Okay, next you look at epsilon equal to half. So you'll get a delta 2. But doesn't matter, your sequence xn is converging to a. So you look at all the terms beyond the n1th term, and you will get another one such that xn2 would belong to a minus delta 2 to a plus delta 2. And for this xn2, what you will have is, it would be a little closer to L. So now you continue this way. At the kth stage, you will have corresponding to epsilon equal to 1 over k. Yeah.
So sir, like, what is the thing that is guaranteeing that delta, this a minus delta 2 and a plus delta 2 would be contained within a minus delta 1 and a plus delta 1?
Okay, you can do that, but you don't need it for this. All we are doing is, we are not using it. Are we using? So what your question is that, what if a minus delta 2, a plus delta 1, and let's say a minus delta 2 is a bigger interval?
Yes, sir.
Okay. Now what I'm saying is, you can argue that you will get a delta 2 smaller, right? That you can always argue, because if in this bigger interval every value is between L minus half and L plus half, you take a smaller one, even then that will continue to hold. So you choose a smaller one.
Yes, sir.
Yeah. Okay. So that's one. But But here for this argument, you don't even need that. I mean, all we have used is that we can choose an n2 greater than n1 such that xn2 lies between a minus delta 2 and a plus delta 2. So even if delta 2 was bigger than delta 1, you don't care anymore. I mean, you just ensure that this is the case. Okay.
Okay.
Because here you already have started with a sequence that's going to A. So you don't need the need to know the delta i's to control the behavior of xn. You are just you're just choosing your xn's appropriately so that the choices give you give you a subsequence.
Okay.
Okay, that's why we are focusing on this condition. Okay, so at the kth step, what is happening is epsilon equal to 1 over k, there would be a delta k positive such that delta k positive, let me not go into such that, etc. And then there would exist n k, which is greater than the previous ones. Such that xnk belongs to a minus delta k to a plus delta k, and as a result fx nk minus L is less than 1 over k. Okay. So what will happen here? So for this fx nk subsequence, what happens? So what I'm asking is, what can we say about this sequence? Not the original sequence, like not the fxn sequence, but this.
Converges to L.
Converges to L. Okay. Now, let's take this, but now I'm not going through that construction anymore. Now my question is, what can you say about the sequence fxn? So here what we just saw is that you can produce a subsequence for which fxn goes to L. But now I'm asking a slightly different question. What can you say about the sequence fxn?
So we know that like limit of fx as x tends to a is L. Then that would mean that limit of fxn will also tend to L. Like will also be L, because as
since xn is a converging sequence,
Huh.
then we say, like, suppose that we take an epsilon positive around L. We say an epsilon positive around L. Then we know that there is a delta positive around X, like around A, such that all elements, for all x's between that, fx belongs to this. Then for all xn's between that, that will be the case.
Just repeat the last part again.
So for all xn's which are between that delta, like delta ball, their fxn will be between the epsilon ball around L.
Yes.
Then if we take, so that would mean that should mean that f of xn converges to, so like the limit of fxn is L.
So no, okay. So let's look at what I did here. So is the argument already present here?
We could say L is a limit point of f of xn because we have a convergent subsequence.
No, but what I'm saying is, see, yeah. So basically, I have kind of distracted you by trying to look at this subsequence. But what I'm saying is, just look at the argument, whether it already gives you what do you want there, that the limit of fxn is actually L. So let's come to the first step, let's say. So here I have written this, but what do we really have? We actually have something stronger, right? There is an N1 such that we have this, don't we?
Yes, sir.
Yes.
Sir.
Okay. So now what does that tell us about the fxn sequence? That fxn minus L less than 1 for all n greater than n1. Okay. So the argument is actually already here. Just that by doing this, I kind of took you away from this, distracted you from the actual argument. So in the second step, what happens? Now tell me. Or the kth step?
We take an so for this for the delta k, we take n to be greater than nk minus 1.
So in fact, okay, you can, but you really don't need, if you look at it carefully. So there exists an nk such that
fn, yeah, for all n greater than nk.
Because here also you will have the same, xn would be this for all n greater than nk, right? So the argument is already here. It's just that by looking at a subsequence, we just completely went off track.
So, sir, we have established that we have a sequence of x's that is converging to A, and corresponding to that x's, we have these function values which are converging to N.
Right. So what we have proved is the following. If x goes to A is L, then for any sequence xn in the domain of F with xn's different from A and limit xn equal to A, we have limit fxn equal to L. So this entire statement, meaning this condition, then after this part, that involves only the notion of limit of sequences. Okay. Now, so what we want to do is actually want to prove the opposite also. So then what would happen is you have a characterization of this statement, limit of fx being L, in terms of limits of sequences. So what we are going to be interested next is this part, this implication. So assume that this is the case, that for any sequence converging to A, limit of fxn is L. Now we want to show that limit of fx is L. So when you are trying to prove such an implication, one way to do this is to go for the contrapositive, right? To show that B does not hold implies A does not hold. So you can try that here. That would be easier. So we had already looked at the negation of this statement, and this is one reason why we did it. So what was the negation of this statement? I'll go to the next page and start there. There exists an epsilon positive such that for every delta positive, what was the last part? This was the negation. You just go back a few pages and check if I have written correctly. Is this okay? Is this the negation?
Yes, sir.
Okay. Now look at it carefully. Now, using this, can one construct a sequence xn such that xn's are different from A, limit xn equal to A, but limit fxn not equal to L? So focus on this part. So for every delta, this is true, right? So let's take delta equal to 1. So there exists an x between a minus 1 and a plus 1 minus a such that fx minus L greater than equal to epsilon. Epsilon is something fixed. There exists an epsilon, right? So that epsilon is for now fixed. So call this x1. Then you look at delta equal to half, then this condition again tells you that there exists an x2 such that fx2 minus L, here it would be x1 since I've changed it to x1, fx2 minus L would be greater than equal to epsilon, and so on. So you keep choosing these xn such that they come from here, and the A point is, I mean, xn's are different from A, and fxn minus L, this difference always remains greater than equal to this fixed positive number. So because of this condition, you can see that limit of xn is A. So here is a sequence you have produced whose limit is A. But for the same sequence, this condition is being violated. I mean, limit of fxn equal to L. This is not true. So, and that is precisely negation of this statement. Negation of this statement is there is a sequence with all these properties that xn's are different from A and limit xn is A. One has limit of fxn different from L. Either it does not exist or it's different. So, and that would be guaranteed by this inequality. So it's the sequential characterization of limit of a function. A function has a limit near a point if and only if you approach that point through any sequence, the corresponding limit is that number. Okay. So I think I'll stop here today. I'll continue from here next time. Any questions or comments? Okay, then see you next week. Bye.